Let's revisit an earlier setup where we have some charges as shown in an XY plane. And this time we will consider what is the potential energy of the system and what is the voltage potential at this point right there. To find the potential energy, let's first start by numbering my particles 1, 2, and 3. And we can find the potential energy of the overall system as simply the sum of each pair of potential energies between particles. So let's solve for U1, 2. We can substitute K, Q1, Q2 by R and solve 8.988 into 10 to the 9 Newton meters squared per Coulomb square times Q1 is 1 Coulomb, Q2 is 2 coulombs, and the distance between them is 4 meters. Plugging this into a calculator yields a potential energy of 4.494 into 10 to the 9 Newton meters, or joules. Now let's do U31 is K, Q3, Q1 over R. And note the order doesn't matter here. We could have just as easily said U13. This is equal to 8.988 into 10 to the 9 Newton meters squared per Coulomb square times Q3, which is minus 3 coulombs, and Q1, which is 1 coulomb, divided by a distance of 3 meters. And this is just 8.988 into 10 to the 9 joules. Negative. And finally, we'll solve for U23, which will be the most difficult one, but not that bad, is K, Q2, Q3 by R. And I should be writing R 1, 2, 3, 1, and 2, 3 for each one, because it is a different distance based on each pair of points. So this is equal to 8.988 into 10 to the 9 Newton meters squared per Coulomb square. Q2 is 2 coulombs and Q3 is minus 3 coulombs. But now the difficult thing we need to find is R23. That's not too bad since we can just use Pythagorean formula to find the distance between these 2 points. So we have a right triangle, and we know that this side length is 3 meters and this one is 4 meters. So in order to find C, we know C squared is equal to A squared plus B squared is 3 meters squared plus 4 meters squared equals 9 meters squared plus 16 meters squared equals 25 meters squared. And perhaps some of you already recognize this as a Pythagorean triple. That means C equals 5 meters. And we can plug down here 5 meters as the distance. Plugging this into a calculator yields negative 1.079 into 10 to the 10 joules. Finally, as the total potential energy is just the sum of the individual ones, we add up all 3 numbers to get a final value of negative 1.528 into 10 to the 10 joules. Intuitively, what this means is that if all 3 of these particles were at some infinite distance away from each other, so this distance is infinity, this distance is infinity, and this distance is infinity, all of them are infinitely far from all the other ones, then to bring these 3 particles from infinity to their respective locations would have this much energy released. It would happen naturally because it's a negative energy, and at infinity your energy is 0. So to go from 0 energy to some negative energy, you don't have to put any work in. It will happen by itself, right? The work will be done by the Coulomb force, and energy will be released in order to get to this configuration. Now, alternatively, you could also say that when going from this minus to the 0, that will take 1.528 into 10 to the 10 joules of energy to bring the particles from this configuration away to infinity. Now let's solve for the voltage or electric potential at that point V. Similarly, V is equal to V1 plus V2 plus V3. So remember that voltage is only dependent on one particle rather than pairs of particles. And so the total voltage at that point will be dependent on the voltage potential it gains from each charge individually, and then summing those up. So the voltage per point can be calculated as K Q1 by R1, Q2 by R2, and Q3 by R3. For this first one, we can substitute in the values. The charge is 1 coulomb, and the distance is the distance between particle 1 and that voltage point. Again, this is a right angle triangle, and this is the same 3 meter, 4 meter one, so we know already that our hypotenuse will be 5 meters. That's the Pythagorean triple. You can memorize that, you can work it out, or you can just realize that this diagonal distance will be the same as this diagonal distance. So we will put 5 meters down here and obtain our final voltage of 1.798 into 10 to the 9 Newton meters per coulomb, or the unit volts. Now we can repeat the same process for the other two. And summing all of these voltages or electric potentials together yields a final value of 1.049 into 10 to the 9 volts. So we have a positive electric potential at that point due to the other 3 points. And again, this is assuming that the voltage at some infinite distance from all 3 of them is 0. So these are our final answers.